concept in this project and how is the consortium aligned around this concept. And starting now on the left, we're starting with steel rolls, raw materials, different possibilities here we evaluated in the project, followed by a coating done by Sandvik. Here the idea is to apply a coating on the steel which then makes the steel survive the harsh conditions you have in solid oxide fuel cell stacks like 700-800 degrees. Once the steel is coated, again it's a roll-to-roll process, a coating process, we try to shape and stamp out these coatings and then apply a contact layer, this is done by Technic Italica, the second last step here on the line, and then finally have a proof of concept in actual SFC stacks by two manufacturers here, Sunfire and Solid Power. And this whole thing is also combined by a cost analysis carried out by AVL. Yeah, so you can see the complete value chain basically is covered in this project, and you have European stakeholders from the industry along this line. So that's very nice. How did we do? Now looking back after the project is finished, one slide on the first aspect to achieve a high fracture toughness. Here the project was to increase the strength by 300%. Very shortly how our approach was. Basically on the left you can see, don't have a pointer, right? No. Yes, so the concept is you start putting a paste of metallic particles, in this example here copper and manganese, between your cell, that's the dark gray figure here, onto your, between your cell and the metallic interconnect, and up on temperature increase and some pressure applied, these metals will react with each other and oxidize, and that is combined by a volume expansion, plus then a reaction on the cell interface and the interconnect interface, so you create a very strong bond, ideally, and the result was in a very high conductive spinel. And we call this concept reactive oxidative bonding. And the summary on the strengths is summarized on the slide, on the figure on the left. What you see as a dotted line in blue, that's a project target. And on the y-axis you have the mechanical strengths of this interface. So everything above that line is stronger, and you can see different compositions. I'm not going into detail here, but a lot of them were significantly higher than we were hoping for. And also not only directly after assembly, but also after aging for 3,000 hours. So demonstrating long-term stability of the solution as well. So these project targets we nicely achieved quite early. And as you can see in the corner of this graph on the right side, that's a standard solution used today or at the point we wrote the application. So a huge improvement here. Moving on to the low-cost sealant coating. Here the overall idea was, can we use steep shields to make interconnects? Normally steep shields equals to low content of chromium, and there are several steels listed here. Basically, the further you go to the right side, the more expensive the steel gets. Chrofa 22 is a special alloy designed for SFCs, has a rather high chromium content, and then you have other steels like 441, 431. That's commonly used steels in the automotive industry or something you would find at home in your dishwasher. So they are much cheaper. So the question was, can we upgrade these cheap steels simply by applying a coating? And we tried this method developed by Sandvik, applying a syntheria coat 10 nanometers followed by a cobalt coating 600 nanometers to ultra thin by PVD in this roll-to-roll process. And surprisingly, that's shown in this bar graph on the rim left. The ASR, that's a Y scale, looks more or less similar for all the steels. For the expensive one, the same for the cheaper ones. That's a pretty nice result, because they have definitely different costs, but if they have the same performance, the same corrosion behavior, I mean that of course offers the possibility to save some costs. And there's one outlier, 431, I'm not going into detail, but all in all the message here is, by using this coating, even at 800 degrees, which is pretty high for this application areas, you can achieve a significant reduction in ASR and show some decent stability. And that can be explained simply if you look a little bit further into the corrosion behavior. So on the left, shown only for 400 hours is the mass gain. So basically if you put a steel chip on, how much mass does it gain over time? Plotted here as a function of time. And of course you want the graph which is as low as possible. You can see uncoated materials, they differ terribly. Once the coating is applied, and that graph on the right side is actually for 3,000 hours, you can see they behave very similar. So this coating is a very effective corrosion protection also for cheap steels. Yes, so how does it translate into costs? You have on the left side the €5 bar, that's the project target. And then we have split the cost into material costs, manufacturing cost, then you have overhead and profits, and then added up to the total cost. So the total cost should be below the line of €5, and for state of the art, as you can see, the total cost is a little bit higher. If we imagine we upscale our low-cost-IC concept using cheap steels, the coating roll-to-roll process, you can see already at a scale of 50 megawatt production capacity. That's not a lot in these days. I mean, other companies now announcing gigawatt scale, so it's definitely even not on a high production volume. You can already achieve these targets, and the most saving potential is on the material cost if you use the cheapest steels. What you also can see is a little bit more expensive in overhead and profits, the orange bar. And that's because you have more stakeholders involved. They want to have a share of the cake and do some profit. So the more stakeholders, if they're more expensive, it gets. And another way to present it is shown here on the right side. So the red line is 100% state-of-the-art reference. And then again, these different domains, material costs, manufacturing costs, overhead and profits, and total cost compared. Red line, state-of-the-art processes, total costs, and then the blue bars is the low-cost-IC things. So also that has been achieved, and again, the clue here was cheap steels, cheap coatings can do the trick. So there's a reduction. Then we were asked to provide some risks and challenges learned. I think the challenge was the implementations from the lab to include those in the production line of the stakeholders. So we tested these new solutions in stacks from Sunfire and in solid power, and in principle they work fine. It's just you compete with a process which has been developed over years. So of course there's room for improvement, and here I think it's important to align expectations between academia and industry. But I guess most of you have encountered these challenges. And the learning is that a cheap steel with an effective coating has potential in decreasing the SOC manufacturing costs. And I think most of the stakeholders in the field are moving or have been moved to these cheaper steels already. And of course, to validate this, I think more proof of concept field test would be the logical next step to demonstrate. How do we exploit these results? So for these cost-effective alloys, these will be announced now on the home pages and promoted by the companies Amparam and Centric. And of course, the impact here is hopefully cheaper manufacturing cost. And this contact solution for this reactive oxidative bonding, here we are in contact with 3 European suppliers for ceramics and pastes who we hope will distribute these solutions for us. And here the impact would be a longer lifetime and increased robustness of the technology. Yes, and that was my last slide. Thanks.
Thank you very much. We have the time to take a couple of questions. So first of all, are there any questions here in the room? Anybody that has something would like to clarify? Maybe while people are thinking about it. Well, first of all, congratulations for the very good results on a technical level. So you said you were cooperating with Sunfire and Solid Power, that you have done the integration in their products. Do you know what's the next step in terms of exploitation? Is there the interest to fully integrate the new interconnects in their production lines, or can you tell us something more about that?
I think we could, if you compare the results on stack level, the improvements are not that impressive yet. So I think there's still some reluctance to take over these results, because compared to state of the art, if you have it on the complete stack level, it's probably not so attractive to change yet. So I think proving it on a longer scale, and that would be the required step here. Yeah.
Okay, so if we were to follow up these projects with another project, allocate another funding specifically to this, where would be exactly the priority that you would see there? Still for the research in the alloys, or how would you shape it to do the next step to make it more attractive for?
Yes. So these findings that also these really cheap steels have potential, that came rather to the end of the project. And we did not implement these results in real stacks. So taking the best ones and then really making a few more stacks and having them long-term running would be what I would suggest would be most valuable to demonstrate the potential.
Okay, perfect. So there is still potential ahead
Oh,
to
yes.
be
Oh,
explored.
yes.
Okay, that's great to hear. So has anybody in the meanwhile found the courage to put a questions or no? Everything was clear? Okay, so we need still to warm up a little bit. So thanks a lot,
Yes.
Ragnar. That was the first project, LOWCOST-IC. Thank you. Now I would like to invite to the stage Silvain, that is going to tell us a little bit more about this project. I always loved the acronym MAMA-MEA. So this is about mass manufacture of MEAs using high-speed deposition processes. Silvain, tell us a little bit more on what you have achieved in this project.
Thank you, Pietro. Pietro has been promising me an entrance music since we started MAMA-MEA. I was requesting ABBA for me to work in, but he's actually pointed out that Theresa May did this, and we might as well ignore short-lived Prime Minister at this point and start with the presentation. So MAMA-MEA. So MAMA-MEA is finished. So we entered the core topic in 2017, and we actually finished last year. So the partners were the Fraunhofer ENES, INEA, Johnson Matthey, NetStack, Systems Group, TU Chemist, Technical University Chemist, and Unimore, which is the University of Modena. So what is MAMA-MEA besides a very entertaining name that people tend to remember? It's trying to turn manufacturing inside out. So those of you that know a little bit about CCM manufacturing, either for PEM or electrolysis, knows that it's primarily a batch process, which is you either start from a film and you start printing your catalyst layers, then you make your membrane, and you make second layers, then you can combine them, or you can print directly onto the membrane. But if you do that, you have to print onto the membrane, you then have to be able to reverse, dry, then reverse your membrane. It is not very good as a continuous process. So what we wanted to do when we started creating MAMA-MEA is, how about we start the other way around? How about if we start with a support material and we start building the layers upward? So either your anode and your cathode first, and then you're going to make your membrane, make your next layers. You can even along the way actually print what we call the seal or the edge protection layer. So this is a layer around your CCM that provides structure to your individual final component. So this is really what we wanted to look. So this is really more a concept demonstration of a very, very different way of manufacturing CCM. And the little drawing here on the left-hand side is how we envisage such process to be, which is totally linear, where you're going to be depositing each layers one after the other with a drying step in between. So these are the KPIs. I'm not going to spend a lot of time on KPIs because this is not a project-driven, KPI-driven. Sorry, Pietro, this is more a demonstration of being able to reproduce what a baseline material was. So this is really the KPI was, can we actually prove that concept? So it systems achievement to date, but actually it should be achievement full stop in here. So what I have here on the right-hand side, if you have a look, is the different passes, how you're going to be able to manufacture. So we've done a total of 14 trials during the projects. When we talk trials, we're not talking benchtop trials. And those of you that have worked with us in different projects know about our development coating line. So what we have developed along the years is an analog to our process, the main process line, at a much smaller width, so we don't waste as much material, but we can also be able to demonstrate various different technique and various different material. And this is what you have here on the right-hand side. And you can see the different passes where, unfortunately, you're always printing black on black. So you got to trust me that each layer that you see one after the other is another layer. So you start with your anode, then you're going to start what we call the capping layer, which is a layer of ionomer. Then you're going to add your support, and then you're going to actually coat your support, and you're going to add another capping layer, then your cathode. But more of interest is the little SCM pictures, which is on the left-hand side, which unfortunately with the light is probably not as obvious. But if you have a look in here, you will actually, the 3 distinct layers actually produce at the end of the process. And if you look very carefully, which is very difficult to see on that picture, you can actually see the support here at the center as well. And this is what the actual CCM is. So we were able to reproduce at manufacturing level exactly what a CCM can do. And the other part that is also very important. So this is what in Johnson Matthey talk, we talked about converting. So when you have a singulated product, that singulated product needs to be supported around the edges. So we all know that a CCM is very variable with respect to environmental conditions. So you need to support that material once you're going to start to use it in a stack, and also provide a surface for your gasket to seal onto. That is really, really important. Now, not everyone uses this as a format, but I think in this case, this is what 90% of the customers, this is what they end up taking. And so what we worked on is, within the same process, can we actually print what we call our edge protection? Can we actually print that support material? And what you have here on the right-hand side in blue is actually a seal printed using inkjet printing. So we can actually do the exact same process where we normally would glue a support material. We could actually print directly that support layer. So again, if you think about it, that's another process that is taken out of the equations that we can add to that continuous process. It makes a big difference in terms of what you can do, but more importantly, it's also reduce wastage. Because in CCM manufacturing, something that people are probably not very much aware of, because you end up using a lot of support material on which you print onto, you actually create a lot of waste. So with this method, you actually start reducing wastage. And the other part that we've actually demonstrated, because if you want to produce singulated product, you want to move away from basically printed a black roll, because then you're going to have to cut it and do your converting. So what you have on the left-hand side is actually the ability for us to start, as we move along that additive manufacturing, printing distinct patches. And then you can then print, you seal around it. And then all you have at the back end is you just need to cut out your part and you got your singulated product. So that is a huge advancement with respect to the manufacturing of CCM. So all this is all well and good. We are able to print black on black, great. But can we actually reproduce the same performance? And we've done stack testing at NetStack. So those of you that were at the award yesterday would have seen Merit Bodnar as the young researcher for the awards. She is the one that's done a lot of this work behind this. So there was a lot of stack testing being done to actually validate that the products we are making actually perform in exactly the same fashion as the material set we had chosen. So really good success here. And not only this, it's not only beginning of life performance, but we actually were able to test it over 1,000 of hours without any issues. And that's what the process line concept was. So INEA, one of our partners, is a manufacturing line suppliers. So what they then do, because this is still, there was still a concept, is they actually start taking every single element for the plant, cost it, and work out what the line would look like. And this is the design of a roll-to-roll manufacturer. So it says 120 meters square. Actually, this is 40 meters square long. And the cost would be close to maybe 15 million. But that's not taking into account that you've got to add a clean room around it. That's not taking into account that you've got to have all the services, everything else that goes around it. But just the line for a 3 gigawatt per year production. Now, this is not a lot. Think of a battery gigafactory. Does anybody knows here how much a battery gigafactory actually costs? Anybody in? Anybody give me a number?
4 billion euros.
Yeah, it's in the billion range. So you can see how much of a difference does that make. We are not in the same scale, and that's really, really important. Now, when we started this project, another thing that was very important, because when we started, our ambition was to move towards digital printing. And Deborah is there, we're working on Gaia, we're working on Immortal, all of the projects, and this is something that we want to look at a lot further. But digital printing, we always assume was going to be around inkjet. So we've all seen papers on the literature, and we've all seen inkjet layers being printed on little screeners and be able to perform. And that's absolutely fine. You can actually print at inkjet level. You can actually have good beginning of life performance. You can even have good durability. Not a problem. But the reason we got involved with a company that had never seen a fuel cell in their entire life, which is Systems, which is a company in Italy who their entire business is to put inkjet process lines. So they're inkjet head agnostics, and they just put process lines for inkjet. And what we've asked them is, right, we would actually like to move towards inkjet printing. And this is where the challenges comes in. And this is what, if there's anyone here from the industry that works with inkjet head manufacturer, inkjet have huge potentials, but they don't last. In a high volume environment, an inkjet head does not have any durability. And then I'll finish off exploitation. So the main exploitation here is that we're actually taking some of these elements already into our PEM manufacturing, but also these additive manufacturing elements, we're taking them towards electrolysis. Because your electrolysis, you need large width, you tend to have less product distinctions. So therefore, this is something that we can use directly towards electrolysis. So SG Systems is still working with inkjet manufacturer because we want inkjet printing. This is where we would like to be, but those inkjet heads are not durable. So synergies with other programs, and that was something else that was really, really important. So Inspire and Gaia. So we didn't start, we had to start with a material set, and this is what Inspire and Gaia were there to provide us with those material set. We didn't try to reinvent materials. This was a pure manufacturing project. And then volumetric, we did a lot of work on roll-to-roll, and roll-to-roll for CCM is very complicated. All those different interfaces is all about how well you can get the drying, how well you can get the tensioning. Roll-to-roll for CCM is an art very often, more than a pure technology. And finally, we've got another project which is ongoing, which is Camelot. So for Camelot, we want to take the concepts of digital printing and have a look at other technologies that we can use for digital printing away from inkjet, and what could they be, and what can we do about it, and try to demonstrate that digital printing actually in real life, large single cell, and with actually our partners at PowerCell over there in Camelot. So perfect synergy, there you go. So that's what we want to try to do. So dissemination, I encourage you to go towards the website, and there's a lot of news, newsletters, a lot of posters that we have done, so everything is there. By all means, go and have a look at it if you are interested, and don't hesitate to contact us. And that was the team at a zoo. So maybe you can't see behind, but yeah, you can see there are penguins at the back. They were not part of the consortium, I reassure you. We didn't employ any penguins during this program. And there you go. I think it's all over.
Thank you very much, Silvain. Great stuff, very interesting, exciting. Now, before I go ahead with some questions, I also wanted to remind anybody in the room, or also those that are following us online, that Slido is still there if you want to ask also questions, if you prefer that way to put your questions. Now, Silvain, Congratulations again for the very nice results. I'm trying to exactly get a clear feel of where we stand now with this new technique that you have developed. Because on one hand, I got the feeling that there are still some obstacles with the printing heads, their durability. On the other hand, I saw also idea that they already worked this line. Where do we stand? There is more to be done there? There is a follow-up, or can we take away something?
Yes and no, because the line that you've got there only had inkjet printing for the seal. So the rest of the additive manufacturing uses other printing techniques, because we developed that process to be compatible with high volume. So we stayed away from inkjet printing for the catalyst layers in the membrane. So this is directly usable. And this is actually used in our electrolysis plant in Cullen to carry out manufacturing. Because of the width, this was the best solution. Now, in our 3 gigawatt plant that we're putting in Royston, we are implementing some elements towards it. And the main elements that we want to implement is the seal part of it, because that helps us greatly. And the reason why at the main plant in Royston we're not introducing additive manufacturing is because currently it's all down to volume. To put a line like this, you need long campaigns, you need a lot of volume, because you're not going to be changing components all the time. Requires a lot more effort. So currently the industry still does kilometers worth of CCM, but they are in a weeks campaign on which you're going to make components. So they're not going to be months after months of the same campaign. So if someone comes up and say, I want these components and I want that in millions, can you make it for us? We would move towards this type of technology. So that's the reason why currently this is still in the boxes and it's not going to be implemented. But for electrolysis, that's different, because electrolysis has less component differential. So generally, it's the same catalyst layers, it's the same membranes, and it's large width. So that is therefore a lot more compatible to be implemented towards electrolysis.
Okay, so specific demand that would encourage you to make this type of investment is not there yet.
Absolutely.
But it's a bit striking for me, because when I was walking to the expo and I was speaking to some of the producers of different companies, they are saying that sometimes they have to say no to the orders. And also, if we are looking at what is happening in the heavy duty sector by 2030, as we discussed in the past, there are like hundreds of thousands of units of trucks that needs to deploy. That this translates in gigawatt, in million of other components when you go to the stack. So yet this is not enough to push you to make this kind of investment.
Again, that's not true, because it depends. Some people are saying no, it's because the orders are small.
Okay.
So I think my colleague Marjorie was talking on Tuesday on recycling, and if you haven't seen our slides on recycling, I highly encourage you to go and have a look at them. It is down to volume. You're going to put the right manufacturing in place depending on the volume that you are required. We are not when I last spoke in 2019 in front of everyone, the volume requirements were a factor difference than what they are now. The factors that we are being asked to produce are unthinkable than we were a few years ago. So if you come in and asking us for a few thousand, it takes a lot of resources just to make a small order, what we call a small order. So I think it's all down to volume, guaranteed volume, and then we put in the capacity in. The capacity is there. Total by end of 2023, beginning of 24, we will have 5 gigawatt worth of capacity on the ground. So the capacity is there.
Okay.
But it's all down to volume and volume orders.
Okay, that's clear. Thank you very much. Are there any other questions? Yeah.
Yep.
There we go. We have one question there. Thank you.
Tested, and if you have tested such a batches, how you make, I would say, this upscaling and calculations for 3 gigawatt factory?
These are extremely good questions. I don't have all the answers. So we've manufactured in rolls of 50 meter length at about 30 centimeters width. So that's where we had a demonstration. In terms of yield, I think it would be wrong to define yield based on a 50-meter roll. I think it would be wrong for me to give you a yield number, because that would be totally wrong. I think yields have to be looked in kilometers, not in meters. So I'm not going to answer the yields, but our current yields, again, it's not something that I can share, but our yields are improving all the time and are increasing. But yields is not something that we share. So sorry for.
Okay, and it was simply the coating line for seals, or it was also assembly of the frame to the MEA?
So we've assembled MEAs at the back end. So we've done the CCM coating at 50 millimeter, and then we were able to demonstrate seals and stack testing.
Yeah, okay. And the quality control, it was simply gas tightness, or what measure?
Yeah, I mean, yeah, it was gas tight. I mean, if you had a look back at the polarization curves, you will see that our OCV were really high. One of the big advantages with additive manufacturing is that you get very little shorts and very little pinholes, because in effect each layer is self-correcting.
Yeah, no, the question was in terms of quality control measure, you cannot measure every cell after production, so you should apply something different, and it was simply tightness, or how you have simply said, this is a wrong cell, this is a good cell, yeah?
QC, how long do we have, Pietro?
Yeah, not too long.
Okay, you want to escape, I understand. Yeah.
I mean, if there is one big challenge for the entire industry, it is how do we measure inline and how do we measure offline? I think the entire industry is still grappling with how best to address those issues. And I don't think anyone has the right answer. You can do a lot with visual, but ultimately, as you say, you want every single part that come out of here. You would like them to be leak tested, short tested. You would want a certain percentage of it to be able to be cell tested. So we do a certain ppm test based on how much we manufacture. So there's a certain percentage of it that is being tested. This is the biggest challenge that the industry has, and Pietro knows that. That's been the main bugbear of mine, something that we need to be able to address. And this is where we actually need the industry. This is not our core technologies. We need other people to come in and provide options. And we talk to anyone that has any ideas, come and talk to me.
Okay, thank you very much. Great job.
Thank you. So I would like, Silvain, sorry, if I can just, to be fair also to the people who are sending questions from Slido. All of a sudden there are very many. I will just ask you one question. Is the MAMA-MEA technology developed licensable? So can you have a license for that, or it's just
it's patented by ourselves. Okay. I don't think we would license it, no.
Okay, okay. And then maybe just one last question. So which is the size of the active area that you can print with your technology?
It was 200 centimeters square for that stack.
Okay.
And yeah, what we can do, I mean, it was 30 centimeter width, so active area is not the issue.
Yeah.
Yeah, you can do whatever width you
you can adapt it to
that's not active area is not the problem.
Perfect. Thank you very much again, Silvain. Thank you. Okay. So we are now moving from the manufacturing of MEA, and we are going to look into the issue of standardization, which is also extremely important for the whole industry, and the standardization of the fuel stack modules, actually. And we have here Federico Zenith, who is the coordinator of a very large consortium that is working on this topic, and very recently also have achieved some interesting milestones, I hear. So thank you, Federico, for being here with us, and please let us know a bit about StaSHH.
Thank you very much, Pietro, for inviting us. I think I'm the first project that is still running. The project is StaSHH. So the first obvious standard extremes. Well, it was the cold year of 2020, so we started from January 21. We are still running, and we are just about 50% where we run until June 24. We got a pretty significant budget, almost 15 million euros, half of which from I'm told I cannot call them CHP, so it's spelled out Clean Hydrogen Partnership now, and no other official contribution as of yet. Now, as Pietro was saying, this is a big project, lots of people, and in groups we have a lot of OEMs. Volvo in Sweden for construction equipment. They also have Volvo Penta and Volvo Technology along as third parties. Solaris in Poland. We also have some Eastern Europe here for buses. Damen and future-proof shipping from Netherlands for ships. Damen for seagoing and future-proof shipping for inland. Then VDL in the Netherlands doing a bit of everything, but especially buses, trucks, and gensets. Alstom in France for trains. AVL for powertrains in Austria, and you might have not have heard of Cetena, but you certainly have heard of Fincantieri, and they build big ships in Italy. And that's the OEMs. Then we have the fuel cell module suppliers, a lot of known names in this audience, I guess. The Ballard, based in Denmark, at least for Europe, Intelligent Energy in UK, Toyota based here in Belgium, Hyundai in Germany, at least they are opening now a subsidiary there. Freudenberg, Proton Motor also in Germany. Plastic Omnium is supposed to be a French company, but the part we are working with is in Austria, and Nuvera based in Italy. By the way, I just worked through the expo area, and both Freudenberg and Nuvera have their StaSHH compliant units on display, so you might have want to pay them a visit later. And then we have several research institutes that usually function in the project as work package leaders. VDL also has a package, otherwise it's CEA in France, Waterstof, which is actually the Hydrogen Association in Belgium, especially Flanders, TNO Netherlands, SINTEF, that would be myself from Norway, and FEV in Germany. So yeah, as you can see, that's pretty crowded, and it was quite a challenge to start in a Corona year when we couldn't meet. So there's a lot of people I know more by the sound of the voice than the face. So what's the point of the project? We have all heard, we keep hearing and here there's a lot of folks in the heavy-duty sector. Mirella this morning showed in her slides that there was all these folks in heavy-duty, and cars not even mentioned anymore almost. But this focus is not on one market. There are many heavy-duty markets. There's one for trucks, one for buses, ships, and so on. And all of these, in terms of numbers, are smaller. A good car can sell millions. You won't make millions of ships of the same type. There's also a much wider range of requirements. They work in different conditions, and every time you have a new module from a new supplier, until now you had to re-engineer the whole thing. So you had to get your engineering team, talk to the other engineering team, and build a new prototype. This meant there were a lot of barriers to competition between fuel cell suppliers. You can think, for example, of Alstom and Cummins. Together they developed those very successful hydrogen trains, but they developed that together, meaning that it's not so easy for Alstom, if they were unhappy, God forbid, if they were unhappy with Cummins, to shift to someone else. But that, of course, could be a problem in other situations. But with a standard, you can solve a lot of this. So you can pool all these markets. You have the same units that can be installed in any sort of applications. You can stack these units to obtain units that are bigger and deliver more power. And by the way, Freudenberg are exactly that down in the expo area. So they have very ridiculously large unit for up to 4 megawatts, stacking up 100 megawatts units. And since you're making always the same units, you can also more readily reach the threshold for mass production, and then automation, and then reduce the cost even further. You also make it a lot easier for OEMs. If they know what they have to install, they don't have to start a lot of meetings with another engineering team and agree on what the interface will be. They know that is the interface that to work with, that's the interface they are going to have to implement. This will also allow free competition among different FCMs. If you're not happy with one, you go to another. The same for opportunity for good FCMs to steel customers from other ones. This will also simplify the supply chain. It will be easier, for example, for OEMs to just detach a fuel cell unit that doesn't work and just send it to the manufacturer for repair and stick in a new one. And all this then should lower the general total cost of ownership and give this economic incentive to kickstart the heavy-duty sector in fuel cells. So that was the main idea of what we like concept. So what are we going to do in this project specifically? Well, the most important thing is defining the standards, and there are three aspects that we identified. One is the size itself. The requirement was a maximum 3. We do have 3, but they are very similar. Then the flow interface, that is how the air goes in, how the hydrogen goes in, how the water comes out, and so on. And then the digital interface, that is how do we communicate to the module, how to do things, how to increase power output, and so on. The projects are built and commissioned 9 modules from 8 companies. Nuvera will build 2, everybody else is going to build 1. And then they will be tested separately at the TNO FEV, so they'll be tested by independent actors, so it will be an objective testing. They have a number of other activities. We also demonstrate the operation of that FCMs, prepare some manual for best practices focused on OEMs to make sure they know what to do with the standard. There's a regulation of codes and standards overview. This was already published. It's on our website, StaSHH.eu. It's a very detailed document. That's 599 pages. And of course, in general, disseminate this standard, which is the main exploitation activity as well. And yeah, in the figure there, that's the most critical dimensions. That is a European truck. European trucks are particularly important because compared to American trucks, European trucks are really tight. And if you want to put a fuel cell module, you're going to have a lot of restrictions in terms of size. So, speaking of the size, in general, the standard documents, we are going to produce 4 of them. 3 are already done. And then the last one will be updated standard at project end. So we'll put together all the experiences and maybe we'll put some more detail or we'll take out some detail from that maybe was not necessary. For the size, we very creatively named them A, B, and C. They have the same height and the same width, 340 and 700 millimeters. And I actually was hoping we could have 680 millimeters. We had a discussion down to the centimeter level, so we fought for every one of those numbers. But the main reason why it's 700 is that that's a width of a bay in the side of a European truck, and the reason is 340 is that 680 is the maximum height in the same place. If it's 181, then it's outside the boundaries and could touch the asphalt. But then if you assume that 340 is the unit, then you have the dimensions are easy to remember as 1 for the height, 2 plus for the width, and 3, 4, 5 for A, B, C respectively. And of course you don't have a D because it will simply be 2 A's in front of each other. The placement, there are also the, you can see also some compound sizes, AA, BB, and BBB. These are the ones that the industry is most interested in. The AA and BB are very good for the size of a European truck, and the BBB for the engine bay. There is no reason you could have a CCC or anything else, but that is the sizes that for now the industry wants to pursue. Flow interfaces can be on 1 or 2 sides. If they're on 2, they're going to be redundant. And we only specify the area of the interface, not exactly where each interface is going to be. We didn't specify where the hydrogen is entering, where the air is coming out, and so on, because it's fairly easy for an OEM to move the pipe a few centimeters on the side. It's not so easy to go around the entire block. Digital interface is defined on top of CAN bus. It follows SAE J1939, which is a well-known standard, and requires 18-pin connectors. Even here as well, we didn't specify exactly which connector because it's pretty easy to adjust. So, commission modules, well, we have something that was delivered by Plastic Omnium. They were very early to deliver. Of course, it's also a question of how much the project aligned with the internal schedule of the company. Plastic Omnium was positioned optimally to deliver early. We initially had 11 fuel cell module suppliers, and now we 8. We lost 4. They were all 4 SMEs critically. We currently have only 1 SMEs left, that's Proton Motor. Also Hyundai joined after these 4 left. And we expect to receive these fuel cell modules in the first half of next year, after which they will be tested. So we generally experience some post-COVID issues with the supply chain, but it has gotten better over time. It was not as bad as we thought it would be, so we just got an extension of just 6 months. We noticed that all designs have some deviations from the standard already. Most of them very minor deviation. Some are downright silly, like so one drain was 1 millimeter too wide. These are obviously no problem, but some have been major, but all of them seem to be fairly easy to remedy. Testing, we have not started yet, but we are soon going to commission these test beds. There are 2 of them. They both built a FEV. One will be deployed at FEV themselves and one at the TNO. They are rated up to 200 kilowatts. They have a 2-axis tilting device to test for maritime conditions. And they will also test 2 of the FCMs at both sides to make sure that the results are consistent. So this is work for next year. Yeah, I think finished early.
Yes, indeed. Thank you, Federico. Really good to see that you managed to find a synthesis and agreement and to define those standards. How difficult it was, the discussion?
It was, well, it was awkward, especially because, of course, you remember that thing about the bat and the armadillo a couple of years back, and we couldn't meet with the entire consortium, not even for the proposal stage, not for the first year of the project. We met everybody first time this June in Eindhoven. And that was a bit difficult. We had with this kind of consortium where we have maybe 100 people showing up at the General Assembly, and some people are more confident and talk very easily over Teams, but a lot of people that just tend to retract a bit in background. So it was difficult to maintain good communication inside the project.
Okay, but beside the specifics also of the COVID, I'm asking you this because I'm trying to guess how difficult or easy do you think it will be, these future standards, once you finish the project and you have validated them also with the testing campaign, and then the next step is really what you mentioned earlier, the exploitation, to convince also those that were not part of the consortium to pick them up, because we want this to be the standards for the technology, right? So how do you see these next steps?
Well, we do have plans to propose the standard to some standard bodies. Of course, we cannot guarantee they're going to accept because it's outside what we can guarantee, but we have several people, especially in the CA, who are strongly involved with these standard bodies. And of course, if anyone is interested, please drop me a mail. You can join the exploitation group of StaSHH, so you'll be updated regularly. You join the exploitation workshops. That's of course all free or paid by you guys. Thank you. And of course, if you have comments, if you have suggestions, they're all more than welcome.
Perfect. So, well-received invitation. We have another question here from the first line.
Thank you. You have indicated that the tests or the modules will be tested. I understand Plastic Omnium has already integrated the module on board the truck. Will the other module be tested in trucks and even other applications, maritime, in trains?
That specific test was something that VDL was doing a bit. They're very enthusiastic, the guys on VDL, I have to say. They can kind of run ahead of the project. The tests that are going to be officially part of the project will be on the test beds, on those specific rigs that I've shown a few slides back. But that test was something VDL was doing there. On top of that, there will be an extra test run also by VDL on some special vehicles, possibly in the port of Rotterdam. We are waiting for confirmation of that on these large autonomous container transports. We are not deciding exactly who is going to deliver the system. Depends a bit on who is ready when. But not all of them will be tested on field. We don't really have the budget for that.
Perfect. Then if there are no other questions, thank you very much again, Federico, very interesting. And last but not least, I would like to invite Karl, that is going to tell us a little bit more about yet another project, still manufacturing, different angle. In this case, we are not looking about MEAs or the modules, but we are a little bit more focusing on the balance of plant, on the different components that go for automotive application. This is the in-balance project, innovative cost improvements for balance of plant components for automotive PEMFC systems. So thank you very much, Karl, for telling us a bit more about it.
Thank you, Pietro. Good afternoon, everyone. Karl Samuelsson, PowerCell, as mentioned. If we go into imbalance, this was called quite a long time ago, 2016. It is a completed project. It was 75% funded, as it's not as much innovation as it is implementation, bringing partners together. We had partners all across Europe, as per normal. It was ourselves, CEFT, CEVT, China European Vehicle Technologies Platform. That's a technology integrator between Geely and Volvo Cars. Standby, Celeroton, Brose, DLR as a research institute, ABL Austria, AESA as being the coordinator, and University of Catalonia. Here it was for many of these parties where this was their first opportunity to dip their toes into hydrogen. For some it was a longer stretch, some it was a little less. And everybody was developing their own parts. I think this picture is perhaps more telling. We had a thermal management system developed by DLR. Of course, thermal management within a vehicle is very important. With fuel cells, that's quite usually the challenge and defines very much of the system of what you can integrate on sizes, as the cooling window that you have for fuel cells is rather narrow. Cooling is very important. A cathode module to maximize your volumetric efficiency, you have to pressurize, hence the cathode system and the turbocharging is very important. This has to be clean air, non-contaminated, so it's quite a specific machinery needed in this. Anode module, how we get the hydrogen in, there's different technologies for this. This was provided by ABL, a rather novel idea. And the control system was developed within the University of Catalonia. I think moving more text, but all the different modules were done by the different parts. We see the ejector for the hydrogen injector and ejector. So you have the full recirculation within that module that was done by ABL. New compressor derived by Celeroton. Compressor with inverter, a very important component. We have the cooling module developed by DLR. Here it's, free water in a car is a big no-no because you can never control when you're going to be in hot and cold conditions. When you sell a car, you never know if it ends up in Spain or Siberia. So free water is very important to have control of. So that's why having the water out after use is very important. So it goes for cold storage, and it's something that consumes energy. So this is something that needs to be taken quite care of. all these things are fine. Then you have to put it into a car, and this is also something we had much of the initial development work as we were early on in this project that was done as per normal. Then came COVID, and then we had to integrate this by DHL essentially, which was quite the task. So that was done very much at our facilities in Gothenburg. When putting things into a P&ID diagram, things look quite simple. Not only did we have to manage the fuel cell system itself and its high voltage integration into a vehicle, and that said, an existing vehicle that we could not modify to what it was. So we had to take something that was available. We had to put in a hydrogen storage system as well. So it all gets rather sticky, as you can see in the bottom right-hand corner of the slide. So, of course, done in steps. First, very much in theory, a lot of CAD work had to be put into. We did not have a lot of space, so this was rather tricky. We had PowerCell, we provided the stacks, we did an enclosure. We integrated this. The third part is actually at our facilities, so it's hand-built. We could test it as it is. The interesting thing with fuel cells is you can, once you've done the fuel cell testing sort of in our labs, the integration step, other than getting it to fit into the car, is quite simple. So when you come that far, vehicle integration and actually producing vehicle results is quite simple. That said, so this was all assembled at our end, put into the car at CEVT, integrated with the hydrogen storage, and then we put the front back on, and managed to get a fully functioning vehicle within all parties. So this was all the modules, all the extra kit, and all the software put together, integrated into the vehicle. And in the end, we did manage to get the fully functional vehicle with all these different partners that really had not done a whole lot of hydrogen work before. So this is at the CEF test grounds outside Gothenburg, on an old airfield. So we actually got it to run. And finally, as you see in the lower hand corner, we managed to get it into a lab environment at Chalmers University, and also in Gothenburg. So fortunately, we had much facilities close by, so we didn't have to send things and people all across Europe. And we actually managed to run a WLTC cycle with a load following system. So we are actually pushing the controls to their very limits, essentially, to run through this whole thing. And that's essentially the crown jewel of the project, that we actually managed to run it all the way through with all these partners coming in. So it was quite the task. The vehicle is now dismounted, and we still have the system in our hands, so that we continue to take a look at it. But in the end, we were successful, even though quite a lot of hurdles on the way. COVID did not help, but we managed quite well. And that's about it for me.
Okay, thank you very much. Interesting overview and to the point. So, one question from my side. You have been working on very many different components, like the thermal management, the anode and the cathode module, but are all these meant to be always together, or could you also commercialize them as separate innovations? Or is this just a concept of how you would do the integration of the whole BOP?
I mean, at the moment, the supply chain is developing quite rapidly. When we started this out, it was really a question, what can we get our hands on? There wasn't all that much choice. That's changed dramatically. That said, it all comes down to actually who's closest to industrialization. Prototypes is fine, and then we have to take it to low volume at least. And then you have to actually have the technology that can take the step, and that's not always apparent. And this was for many of the partners here, it was a first step to take a look at what we can do, because many of the OEM, the traditional suppliers these days, they are moving into hydrogen quite heavily. This has become very evident as of late, because this is a business that is growing, and the availability is very, very different now than it was then.
Yes. And how much of what you have developed for this platform, for this specific vehicle, would be also interesting for the larger duty, heavy duty applications that you saw that there is a lot of interest now that are going really there. So
I think of the OEMs that were in on this, they have Celeroten still moving into that. This is they are continuously developing their business. As per se, AVL does not make parts in that sense, but this is the technology that is moving forward. So at the start of this was very brand new, so to speak.
Okay.
So this is what is going in.
Okay.
So everything that we've seen here has been moved forward. Maybe not exactly by these partners, but it is definitely moving on. So
Okay,
this is
so
not
solid
just something.
basis.
This is not a bunch of fun ideas that sort of just watered out and ran out into the sand. These are progressing, and you're seeing developments on that, and you know, on the tier 2 and tier 3 level as well, because these are all put together components.
Okay, perfect. So let me see, I received a question from the slide. I'm going to read it with you. So could air conditioning be accomplished using, oh, it disappeared. Thank you. Okay. So now it's slightly changed. So could absorption air conditioning be accomplished using spent heat from fuel cell? If yes, will this become integrated into the modularized package?
That was a very specific question. The heat that we do produce, I mean, we look at it in different applications. You look into these sort of thermal recovery. It does depend on the quality of heat and the level of heat that you're going into. So I think from a technical perspective, yes. From a practical perspective, it is a bit tricky because you have to sort of maintain a certain level of heat going across. So not that I'm the expert on this, but there is, of course, going forward, there is much more opportunities of integration that we haven't even explored.
Okay, perfect. Well, then, thank you very much. Unless there are questions in the room, but I don't see anybody raising their hands. All right, so thank you very much, Karl, again, for the overview and the presentation. All right, so now we enter into the phase of the debate. And again, you know, much of the debate, I will start by putting some questions, but you know, if there are things that you are interested about that you would like to discuss, please feel free to jump in. Now, first of all, I will also ask to our colleagues at the back if our colleague Ravi has joined us remotely. Okay, I got a thumbs up. So there we go. Ah, perfect. So allow me to step in here. So as it was mentioned, as it was mentioned earlier by Mirella, we are also trying to involve some additional views. So not only from the people that have been working with in our projects, but also to involve the wider scientific community into this debate, which is the reason why we have also invited Professor Ravi Thampi to join us for this debate. Ravi, good to see you and good to have you here with us. Can you hear us and see us fine? We can see you, probably. You. Okay, yeah. Very perfect. So just a quick word, Professor Thampi has over 40 years of research and experience in the field of renewables and hydrogen. He's currently a professor and former vice principal of the Internationalization for Engineering and Architecture at the University College of Dublin in Ireland. And he's there teaching renewable energy-related theory and chemical processes, applied chemistry for engineers, and micro and nanomaterial science. Ravi, I just took like a brief extract of your CV. I hope that I managed to capture a little bit what is your expertise and what the reason why we wanted to have you here also with this debate. Even though we couldn't see you during the presentation of the 4 projects here, I assume that you were here with us and you could hear a little bit what has been said. Perfect. And I think that I would like to start a little bit this debate with a broader type of question, which is we just touched upon very little. But if we're looking at the demand for components that we are expecting in the coming years, in the coming decade, do you have the feeling that the manufacturing capacity could be a bottleneck for the uptake of fuel cells and hydrogen technologies in the different end uses?
Thank you, Pietro, for a nice introduction. Can you hear me?
Yes, we hear you fine.
Actually, I think there are no manufacturing limitations in Europe. I think there is no will to manufacture in Europe. I think I would like to define it that way. That's simply because, as we had a private discussion earlier, I think the main issue now is that most of the capital is international, and they look for profit, and therefore you take it to the place where it can be apparently made cheaper. So this is actually the main problem in Europe in my understanding. So if we really want to make fuel cells or any hydrogen energy components or the entire unit, standalone unit, there is a definite capacity here which can also be raised for the domestic market. So I will discuss a little later maybe the difference between the domestic market and the export market. First of all, there is a huge market in Europe for domestically for these products. So if we can really meet those demands, then the export market can be done differently. For example, it can be directly exported, at least partly, or it can be licensed to other countries where it can be made locally for cheaper alternatives and sell it locally because of the exchange currency exchange differences. And then you can also make it probably, if the company is big enough and have the capital, it can be made in a different country for the local market. So I don't really think there is a limitation of manufacturing capability in Europe. We need a will to do that.
Okay, thank you very much, Ravi, for this starter. May I ask also to somebody from the panel if you would like to comment on that one? Silvain?
Okay. So, supply chains. So that's the first limitation. So very often we look at the system from the top end. So you get commitment from governments to put buses, to put trucks, to put electrolyzer in. Below that, you need to make the profile plates, you need to make the MEAs. Below this, you need the ionomer, you need a substrate. So all that supply chains needs to be energized in order to respond to the capacity. And that is not necessarily elastic because some of the capacity is actually limited. And I've mentioned earlier that it's all down to volume and volume commitment. So until you have a CapEx commitment across the board, it's a bet from the various different companies in order to put the capacity in to respond. So technically there are no issues to do it, but the commitment and volume commitment is what's holding everything up. And it's also holding the cost, because until you've put in the capacity on the ground, until you put the substrate of the ionomer manufacturing on the ground or the CCM manufacturing on the ground, then your costs stay high. So it is, to energize that TLI, it is be able to have commitment across every single part of that supply chain. That's how you address your demand and capacity.
Okay. Are there any other comments? Because otherwise, I seem to have to understand here that there are no technical challenges per se.
No, I would tend to agree with Silvain. It's not technology that's holding us back or immaturity. That's by no means the case. I think we've proven that essentially the stack technology, which is actually born out of the FCH-JU, can't be said otherwise, that we are cooperating with Buche. We are putting that into production. As Ravi said as well, it is about a will to want to. Otherwise, it will go as all other technologies have gone. It's easy to go east. As you pointed out, Silvain, it's not a big investment thing either. It's not It's not a giga battery factory. These are reasonable things. Machines that cost the same everywhere. They're made in one place, so they cost the same more or less wherever they go. So it's where we want to put things. In our will, we want it here, and it's important that it's made X, Y, Z. But otherwise, we're not looking for a technology breakthrough. Quite the opposite. It's a commercial breakthrough. It's volumes. Okay. Fuel cells has the fantastic advantage that on the repeat cell level, I mean, in a car, you have to look really hard for a part number that is repeated 400 times in one car. So in one car, you have 400 of one thing, and then you do 1,000 of that, voila, already there you have essentially an automotive volume of hundreds of thousands for one piece. So you get very quickly to a volume scale. We just have to get there. But it's not a technology breakthrough that we're looking for.
Okay, Ravi, are you still here with us?
Yes, I am here.
Okay. Okay, good. So we will maybe also get back to that one, but I also wanted to ask you another thing, Ravi, still on your opinion. If you're looking a little bit at the European industry versus the rest of the world, do you see that our competitiveness is under threat? There are sectors where we are the leaders and we are risking of losing this leadership, or sectors where we should become the leader and we are not there yet? And more in general, do you see a threat for the European supply chain? Because now we have discussed a little bit the technical aspects, the technology point of view, but then it's not only about that. When we are dealing with manufacturing, with supporting the manufacturing in Europe, we also want the European manufacturers to be in the lead. So how do you see this going ahead? Do we risk to lose the supply chain here in Europe as we progress, or are we doing fine there in that sector?
Let us take a decade ago or a decade back in time. We used to make solar cells. We used to make photovoltaics. We used to sell it locally. There was a company called QCell, which used to have a lot of orders, and they used to be number one. And then finally, within a few years, it was sold for just a token €1 to an Asian company. Why did that happen? And that's partly because of wrong market moves, I mean, future trading and things like that. I don't really want to go into that. So there is actually no supply chain issue if there is an industry here which can actually cater to the market here and abroad. There is technology, there is market, there are skilled people, and there is a lot of policy support. So the question now is that if you really want, or if someone wants to really make it at a lower cost and bring the whole thing half the planet, over half a planet distance, and still say that this is going to be for renewable energy and sustainable energy, first of all, even there you are not carbon neutral. So you really go across, back and forth, mine from one place and process it on the other end of the planet and bring it back to the market and then re-export. I think if we really make a good plan, we can develop within Europe a supply chain, and we can definitely make every important part, maybe a few parts here and there, probably we can import, but the core technology and the core unit, balance of plant, everything can be locally made within Europe. And the solar cell is a good example, how we lost that competitiveness to someone else. And if we don't do this for fuel cells and hydrogen, we will rerun the same show, and afterwards we just regret. We develop technology, and then it is either shifted away, taken away, given away, or copied. So we should not do that, at least for fuel cells and hydrogen. We can make mistakes once, but not every time.
Yeah, we shouldn't. Thank you very much, Ravi, for your view. I would like also now to look a little bit at the table, because I remember in the past, it was also mentioned that the manufacturing is not only about developing a machinery that will allow you to then produce easily anywhere else in the world. There is also a lot of know-how that goes into the manufacturing techniques. So what is your view on this one of the European competitiveness?
Yeah, I think
Please,
now looking at the solid oxide technology, I think we have the know-how, we have the capacity, especially in Europe when it comes to steel manufacturing and so on, so that's in our DNA. What I'm most concerned about is how fast can we scale it up. If you look at the hydrogen demand projected for 30, 40, and so on, I mean, how do you get to these production rates? And that's, I think, the challenge, to scale up super fast to be competitive. So everything is there, it just needs to get up to the volumes required.
But what is going to prevent from other players from coming into Europe and provide what they need? Because that's exactly what happened with the photovoltaics. At a certain point we had the market, we had the feed-in tariffs, but it was just got cheaper to produce somewhere else and then to import it here. And there is no particular reason why this couldn't happen also with the fuel cells, with the stacks, looking ahead. So I don't know if there is also something that it's, because a lot of this comes into the policies that are put in place by member states and to the Commission, but what, is there something we could do as a research program that we could facilitate from our end to make sure that everything stays also here?
And I'm going to sound like Yogo, that's going to be hard. But competitiveness, I think it's more a question of where the manufacturing capability will be. I think EU companies will be competitive, but it's a question of will we put the manufacturing capability in the EU? And that's down to two things. First of all, where do electrolyzers going to go? Because where is the hydrogen going to be made? And the Inflation Reduction Act is going to be really important. So that will make, in the US, hydrogen production competitive. So suddenly if you start producing hydrogen in the US, this is going to be generating the market, right? And that is self-fulfilling. This is where manufacturing will go, where the demand is going to be. And I mean, Jonel knows as well as I do, the number of vehicles registered every year, the biggest percentage is in Asia, right? Yeah? So that's where the demand is going to be. So this is what I think the EU has to be careful if you want to retain your manufacturing. So it's not necessarily the competitiveness, because the companies in the EU will go where the demand is going to be. But if you want to retain the manufacturing and therefore the jobs and the know-how, the training, you need to make sure the market is well supported. This is why all the work that Hydrogen Europe does with respect to the AFIR regulations, trying to make sure the infrastructure is in place. Hopefully the hydrogen banks will help, again, ensures that you retain that hydrogen production here within the EU. That's what's going to drive your manufacturing capability. And ultimately, it's all down to business case. It's all down to where the demand is going to be. And it's that simple.
Maybe could point out that you just mentioned that you need know-how, not just things. But I feel a bit guilty because my project is about removing that. So when you have a standard, right now, if you wanted to implement, for example, Chinese fuel cell modules, you would have to have a Teams conference with your engineering team, a Chinese engineering team, with, of course, the time zone difference and difference in languages. But once there is a standard, so we'll be kind of opening a door. So we should make sure that there's not just people coming in through the door, but also we are storming out as well.
But more concretely, is there something that you see that we, as the joint undertaking, besides facilitating this process, we could do in the future for manufacturing? Because I have the feeling, if I look at the recent past, we have done around 8 projects, provided a funding of around 31 millions. And when it comes to manufacturing, it's also a bit tricky to follow the development because there are so many different things. And today I saw we had an example, like we have 4 projects that are working on manufacturing, and you are all looking at very different things, right? So MEA, standardization, balance of plant, SOC. So looking ahead, really, you know, it's a very complex puzzle. You know, you take a stack, you have 3-4 leading KPIs that you can easily deploy and use to track whether you are progressing with the development of that component, so the durability, the power output, and whatnot. When it comes to manufacturing, it becomes also a bit tricky, to say, are we advancing or not? Like you mentioned, for example, in the MAMA-MEA, the scrap rate, you have reduced it to a minimum, but that's for you, that's for your process. I cannot say that in manufacturing now the scrap rate, bipolar plate, GDL, MEA, it's all very, very different. So when we are trying to do a bit of the synthesis at program level of the joint undertaking, looking ahead, how do we make sure that we are pushing the technology and we are pushing the industry that's behind that? Like, so how do we make it also profitable for the industry to indeed to stay into the game and to stay ahead of the game? And Ravi, I see you raised your hand, so please.
Yeah, I mean, coming back to competitiveness, I think the joint undertaking has done over the years a wonderful work and contribution to develop fuel cell and hydrogen market and the policy initiatives to this level. So we are now at a very highly competitive level. Now, how to reap benefits out of it is the question. Now, I have seen over the years the emphasis of the European programs is always towards the SME. There's no harm in that. But SMEs don't have the financial muscle to do large projects and large manufacturing activities in Europe or anywhere. So sometimes what happens is that the SMEs develop IP, they try to exploit, and they may not get the capital to invest. They may not even get the support of the investors. There are no risk takers in Europe compared to, say, in the US. So what happens is that it gets thwarted and someone else will take it over or really copy. So I think at this stage that we have matured into that kind of a technical competitiveness, we should now open up the portfolio to licensing. Earlier, one of the speakers, Johnson Matthey, I remember, they were not willing to license. They can afford to say that because it's a cash-rich company, they can do that. But that's not the situation with SMEs. So SMEs, instead of sometimes when they are not able to move forward, probably it is better to bring it into a pool, and joint undertaking can keep that pool to license them in consultation with the inventor, as well as and also it can act as a bridge to bring in other companies who will have the technical and financial ability to manufacture it, maybe in designated industrial parks in appropriate places within Europe. So I think we need to not only just exploit oneself and themselves, but also be open to licensing within Europe to entities who can do it in a better way. So I think the clean hydrogen undertaking should now become a portfolio of IP market where they can bring in the investors, the industrialists, as well as the inventors together into one platform, try to arrange capital from private and public resources who can take that kind of risk over a longer period of time.
Perfect, thank you, Ravi. Very concrete suggestion. Are there other reactions around the table? Silvain?
So, licensing, if you license, you lose your competitiveness. So that is that simple. Your manufacturing is very difficult to patent because most manufacturing processes are quite well known. So your know-how is key. Licensing, you can license at the material level in terms of how you've put things together. So I think licensing is how you risk losing competitiveness. And to go back to your first question, what can the FCHDU do? I've mentioned it earlier, where there is a technical gap, and you and I have had a lot of discussion before, it's all down to quality control. What can you do inline? What can you do offline? Because you want very low PPM failures in the stacks. How do we ensure this? How do we ensure and that's not only for the MEA here, because the same is true for plates, the same is true across. There are, and I'm not talking about visual systems here, because visual systems geometrically you'll be able to flash light behind and look at any materials that are missing. You are talking about, you want to be able to leak test every single part in theory, you want to short test every leak part in theory, you want to have at least a fast way of having beginning of life performance, so that when these parts goes to the stack manufacturers, they can have certainty that they're not going to have any failures. We can only do that at a certain PPM level, because these are still not be able to be done in line. They're all done offline. So that is the biggest gap. And if we close that gap, that would give us competitiveness.
Okay, so you're insisting on the quality control as one big area where we really in manufacturing need to improve in general. Do the others concur? Would you also?
Again, I would choose to concur. Same thing.
Perfect.
But on the other hand, I mean, as Ravi said, that's essentially what we when it comes to licensing, that's what we did. We, as a small company, focusing on one thing, developed a technology platform that we licensed out to a much bigger player, to Bosch, because they could pull it. As we did not have the muscle to bring it to that kind of level. That said, we still reap both benefits, so we still access to this technology. There's different ways of licensing things and different setups, so it's a business model thing. So because I think on the other side, the larger OEMs are usually very much better at doing what they do. This is bringing something new, so it is maybe not the perfect role model, but it is a model, and I think that there are reasons why this worked that are repeatable in that sense. But on the other topic, I mean, as I mentioned, you very quickly come to millions. So PPM is very quickly the question. It's PPB, it's part per billion. We have to be starting to talk about, and that then when things start rolling, then we have to have that in place. And that's there are ideas and concepts. But on the MA side, it's a tricky part because it's really difficult to find something that really takes you all the way to the full to an assured full manufactured stack.
Thanks, Ravi. I don't know if you also had some questions that we have here. As you see, a very knowledgeable panel, and there was something that you also wanted to ask or discuss with them directly, if there was a point. Otherwise, you know, I still have plenty of points that we could discuss.
No, I just say that I would like to say that when I said licensing, it doesn't mean that override licensing for everything. The companies who can actually develop it to the end has the financial capability to do that. They can do it themselves. But actually, it is a waste of effort, public funds, and years of work if a particular inventor cannot bring that into the market simply because this company doesn't have the capacity to do. So I think it will have to be done with some kind of pragmatism, jurisprudence, and finally, can we make it? So if one can make it themselves, yes, that's the best. But if not, it should be licensed. That's what I wanted to say. So I think probably that explains the idea.
Okay, perfect. Thank you, Ravi. Now I'm also looking to the audience because you know, I don't want this to be just a debate here on the table. Like, I don't know if you have some question, like you have quite some industry representatives here knowledgeable, and I don't know if there is something that you wanted to ask to them concerning the manufacturing. If not, well, think about it. We can, there we go. Here we have one. Sorry, the microphone is coming up to you.
Thank you. So, Daniel Rago speaking from Croatia. I would say that manufacturing is not founded because you are speaking about research days, and the funds are coming only for research and not for manufacturing. So, it means that, in fact, we cannot wait for to have funds to be able to put quickly in production the product we are developing. And that's it. It's to be known. The only IPCEI is a way to get funds for the manufacturing. So we have got an IPCEI for hydrogen. That's good. Europe had done that. Probably it could help to have manufacturing easier done, but Clean Hydrogen GU is just funding research. If I'm not wrong, that was it.
No, indeed. No, but we're trying to find out between the two, like what we could definitely do to also to help, not only to develop the technology, but indeed to help also the players that are behind the development of the manufacturing techniques. So that's a little bit what we are trying to extrapolate. And it's clear that most of the manufacturing will be pushed by industrial policies, which are not within our remit. But yeah, maybe there is also something between what they are doing and the research that where we could help. And I don't know if you have some suggestions or specifically what a joint undertaking could do for the improvement of the manufacturing or quality control, more on the technical side.
It's not so easy to respond to that. What I would say is that probably H2 Valley or the help for the end users will also develop the market. And once the market is taking off, the industrial players will be able to put money in, not through requesting for funds, but their own money. The issue I can see probably now is that if the market is not taking off, we do naturally need public money. But if the market is coming, we don't need that anymore.
Indeed. Yeah. Okay. Thanks. Okay. I think that I squeezed as much as I could from you, from your knowledge, and also from your side, Ravi. Thank you very much for joining us and enriching this debate. I don't know if you have like just some final thoughts, like if there was one key message that again you would like to give to the joint undertaking, because again we started our next cycle for the next 7 to 10 years, and manufacturing is one of our pillars. So some points, SMEs, licensing, quality manufacturing, some of these points already came out, but if each one of you would have like one key message, one key request, or a concept that you would like to be further seen integrated in our future calls, what would that be? You know, maybe Ravi, we can start from your side. Your key advice for us.
I think we need to develop here the availability of finance. When you go to, say, Silicon Valley, you see a lot of investors who are willing to take the risk, even for very large investment. But if you come to Europe and if you are an entrepreneur or a small SMI wishing to make development based on intellectual property they have made, maybe half-baked idea, or even if it is an academic place like a university, there are not many avenues here. So I think one can look into smaller countries within Europe who are industrially well placed, how they do that. One example is Switzerland. I mean, you actually have very many opportunities where you can present your ideas and pitch it and then try to get small investors, afterwards taking into venture capitals and things like that. So I think an organization like Clean Hydrogen Europe, joint undertaking, can organize these kind of, not simply 2 minutes or 3 minutes pitching, but rather an exchange of, I would say, ideas, where you can bring in the different players and stakeholders and policymakers into one place where investment can be channelized, put together, partly by the state, partly by the provincial government, partly by private investors, and a small bit from the European Union and also from the private banks, so that some of the best ideas come into reality and they create jobs, they create products, and they actually put together the necessary supply chain for a thriving industry of hydrogen and fuel cells within Europe.
Perfect. Thank you very much, Ravi. Now I would like to continue on the table here, Ragnar.
Yeah, so I think it's important to focus on the components and materials which have not been upscaled on large scale yet, so which is new, and I think all technologies have something new which needs to be upscaled. So supporting their quality control, I think, is very important there as well, and that's something which can be done from this enterprise. Yeah. And by that, hopefully, then lowering the risk or to invest on a large scale from the industry.
Yeah, the technical perceived risk. Perfect. Thank you, Silvain. You?
For me, it's all about the supply chain. You will not get to your manufacturing volume if the supply chain doesn't come in. So if you wait for your end product to have the financial commitment, then everything else needs to fall in line behind, and they need to be nearly ahead of that commitment. So a lot of the EU targets are for hydrogen being produced or number of vehicles, but everything else behind has to be ready. So your supply chain has to be there, and it will help you meet your capacity, your cost, because if you increase your cost in your supply chain, you will reduce the ultimate cost, and it will enable you to meet your timing. So a lot of what the EU is doing is great, but do not forget that everything else needs to fall in place behind.
Yes.
Don't focus just at the top.
Okay, perfect. Thank you very much, Federico.
Well, one thing that I found myself repeating to several people recently was that the technology for hydrogen is here and it's good enough to be deployed, and most of the problems that are unsolved often are no longer engineering problems, but more like economy, social scientists, politics, and maybe if they have to give one suggestion to the clean hydrogen agenda we're taking, it would be to try to have involve more these sectors of universities and institutes, because we have, of course, plenty of engineers, plenty of electrochemists, plenty of all sorts of technical researchers, but not so much on the soft side, so to say. And that I feel it's a bit missing. So that's maybe it's a more a Hydrogen Valley comment than a manufacturing comment. But I think that part is a bit missing, has been neglected ever since, because it was not necessary in the beginning.
Yeah, so enlarge the community that will enable us to deploy. Okay, thanks. Finally, Karl, do you have some?
Yeah, I'm perhaps taking more of a philosophical picture of it, but I think Europe has to make manufacturing great again. We manufactured here in Europe for many years, and then I don't know who's to blame, but there was a big, I mean, even Swedish politicians were almost happy when manufacturing jobs left, because that was, no, we want just services and apps. But manufacturing is the base, and I think we've neglected that, and that's something that it creates jobs, it creates wealth, it creates everything. I mean, China took 500 million people out of poverty by manufacturing things, and somebody stopped, and now we're saying that that's a problem. We've been able to keep what we got, what we had, the things that were essentially too heavy to move, but those are the incumbent technologies that are sort of moving out. The automotive OEMs are looking, how do we keep people employed? And we have to want to do that. We have to want to manufacture things again. I think that's very, and might sound a little banal, but I think that deep down, we've sort of let that go, and been happy that that goes away, because that was old school. But no, it's not. It is the way we live, and it's something that we have to keep. And how you put that into policy, I'm not sure. Yeah. But I think, Ravi started out. We have to want to do this. Yeah. Because there's really no reason why it has to go away. No. It's not difficult. It doesn't take space. It's not an environmental implication that we just pretend is not there, because we gladly do things. If you don't want to put your kids into a manufacturing job somewhere else in the world, you shouldn't be buying that kind of stuff. We have to want to do that and have it at the same level. Otherwise, you're essentially a hypocrite. I do it myself, so no pointing, no fingers. But essentially, we have to look at ourselves and say that manufacturing is something important, and it's important for our prosperity.
Perfect. Thank you. Thank you very much for these very inspiring final words. And I think that the joint undertakings behind that, well, of course, our task is more limited, is on the technical side. But I think that you gave us several good pointers on what needs to be done, also more what we can do on our side. And I'm afraid that now this is the time we had for, and I don't want also to continue with the tradition of eating to your coffee breaks. So I would like to thank once again Ravi for joining us remotely, and also our 4 wonderful panelists. So please, one applause for them. And thank you also to all of you for staying with us, and I hope it was an interesting debate, a bit different from the technical KPIs we had heard this morning, and now we can all go for our coffee. Thank you.